The commutator gives us a way to express the uncertainty principle more precisely. Okay, so we can postulate now that, okay, if we've defined delta A as an uncertainty in property A, okay, and the way you define uncertainty is this expression right here. This is the average or expectation value of A squared minus the average or expectation value of A squared, and then you take the square root of the entire expression. That's the uncertainty. Okay, if you'd had some statistics, you'd recognize that that's just the square root of the variance. That's really just a standard deviation. Okay, the uncertainty principle shows that the uncertainty principle in this postulate number 5, we're going to call it number 5. That we're making this postulate, which is essentially a statement of the uncertainty principle. We're saying that the product of the uncertainty in A times the uncertainty in B must be larger than 1/2 the absolute value of this integral right here. What is this integral? Integral of psi star. And what is the commutator operator? That's A hat B hat minus B hat A hat operating on psi d tau. Okay, so that's a postulate that essentially states the uncertainty principle. And so we can show that in the case of x and px, that what is the uncertainty? What's the delta x times delta px? Delta x times delta px equals integral of psi star commutator of x and px psi d tau, right? But what is it? And then absolute value of that multiplied by 1/2, greater than or equal. Greater than or equal to 1/2. So what is this thing on the right-hand side? We've already shown what the commutator of x and px is. It's I h bar. So what's the integral of psi star I h bar times psi d tau? This is just a constant. I can pull it out of my integral, right? So that gives me 1/2 I h bar. What's integral of psi star psi d tau? 1. It's normalized. So that's the absolute value of that. Okay. Take the absolute value. So that's that. That's this one. Okay, this whole thing. And so it's equal to this. And what's the absolute value of I h bar? So this is going to be h bar over 2. Okay, so delta x times delta px is greater than or equal to h bar over 2. What's the absolute value of I? That's square root of I star times I, right? That's square root of I squared. Oops. Yeah. Square root of, and I star I is what? I star is negative I, and times I, square root of negative 1, that's just 1, right? So that's just going to be equal to h bar over 2 times 1. Absolute value of I is just equal to 1. So that's your uncertainty principle. Okay? Now let's go back a little bit to that expression for the uncertainty, so you can appreciate where that comes from, how that relates to standard deviation. Okay. What's the formula for standard deviation, if you recall? Sum of x minus x average, right? That's your deviation. So you have a series of numbers. Subtract the mean to get the deviation. You square all the deviations, add them all up, and divide by n minus 1, right? And if you're dealing with a very large number of measurements, you just divide by n. And then you take the square root, right? Okay. So let's expand. What is x minus x bar squared? This is x of I, right? Sum over I. What would that be? X of I squared minus perfect square binomial minus 2x of I x bar minus x bar squared over n, right? Oh, plus, sorry. No. Minus for the second one. I'm sorry. Okay, minus. All right? So we can simplify this expression. We can expand this expression inside. Let's do that. Summation of x of I squared minus 2x of I plus x bar squared divided by n. And you're going to take the square root of that. Okay. This is going to be, okay, we're going to split it up. So this is going to be sum of x of I squared over n. What is that? That's just the average value of the x of I squareds, right? Okay. This second expression right here, minus 2 times x bar. X bar is just a constant, right? I can pull it out of my summation. Like, for example, if I were, let's say my x bar was 3, okay? And so 2 times 3 times x of I, see, it's just an average. So I can just say that's equal to sum of 6x of I, right? And I can pull out my concept from my summation because this is just going to be 6 times x1 plus 6 times x2 plus 6 times x3. So I can pull that 6 out. So that's just 6 times summation x of I. Right? So over here, what we need to do is factor out 2x bar, okay, and then you'll have summation of x of I over n, okay? And what is summation of x of I over n? Okay, I don't put that x of I here anymore, it's just x squared. Right? What is summation of x of I over n? The average, so that's just x bar, right? So what is 2x bar times x bar? This is 2x bar squared, right? Plus summation of x bar squared over n. What is summation of x bar squared over n? What is the summation of a constant? What's the sum of a constant from I equals 1 to n? It's just that constant? That's going to be, okay, let's try it. C plus, for I equals 1, there's a C, right? For I equals 2, there's another C. For I equals 3, there's another C. And so on. How many C's do you have here? N, right? So summation of x bar squared is just a constant. So summation of x bar squared is just equal to, from I equals 1 to n, it's just n times x bar squared. Okay, so this expression right here, this is just x bar squared, summation of, this is just the average, I'm sorry, this is x bar squared, right, times n divided by n. The summation on top is just n times x bar squared divided by n. So your n cancels out here. And so what do you have left? That's just going to be equal to square root of the average of x squared minus 2 times the average of x times the average of x. So that's really just what? To make our notation consistent, let's just call that 2 times the average of x squared. Okay? So minus 2 times the average of x squared plus, and this is just the average of x squared. So that gives you square root of x squared, the average of x squared, minus, we can combine these two. So that just leaves 1, right? So minus average of x squared. So that's how you calculate the standard deviation for very large n. Okay? Now, note that these two are not the same. Okay? The average of x squared is not the same as the average of x squared. Okay? Because let's say you have 1, 2, and 3, for example. Let's say your x's are 1, 2, and 3. What's the average of x? 1 plus 2 plus 3 divided by 3. The average is 2, right? But that's the average of x. But what's the average of x squared? The average of x squared would be 1 plus 4 plus 9 divided by 3, which is going to be 14 over 3. Okay, oh, I forgot. This has to be squared, right? So 2 squared, that's 4, right? But 14 over 3, what's 14 over 3? That's 4 point something, right? So this number is always going to be larger than 0. It's going to be a positive number. Okay? So that is where that comes from. So that delta A we have here, that's really nothing more than the standard deviation. So we're expressing our uncertainty as a standard deviation.